Here's a power series function that is given by only the even powers of x. This should be an n right here. It's a typo in the notes. So that should be x to the power 2n. And we want to show that this power series is a solution of this differential equation. Okay, and so in reality what we have to show here is that if we take two derivatives of our power series function, we should get back the negative of the power series itself. And so that's our goal. So let's just take some derivatives then. So here our power series function, f of x is equal to sum, n goes from 0 to infinity, negative 1 to the n, x to the power 2n over 2n quantity factorial. When we take the first derivative, so in this series, by the way, let's write out the first couple terms here. So the first term of this series is 1. The next term is minus x squared over 2 factorial, which is just 2, but 2 factorial. That's when n is equal to 1, right? Plus the next term here is x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, plus x to the 8th over 8 factorial, etc., right? Minus, plus, etc. And so let's take the derivatives here and see what happens. So f prime of x. By the way, the reason for doing this is that the first time that we do this, we're going to have to consider the fact that there's a constant term here, but the second, after we take one derivative, there won't be a constant term because the next term is still going to have an x, right? So this one starts at 1, the derivative rule, right? Negative 1 to the n over 2n quantity factorial times x to the 2n minus 1, and the 2n comes down, right? And so we've got this. Sorry, the 2n comes down but doesn't go down there. So it's a derivative. So the 2n goes here. And now at this point, when we take the next derivative, so just in your mind you can work this out, right? There's still an x term left here. So there's no constant term. The first term of this series starts with n equal to 1. So sorry, x to the power 1. N equal to 1 does give you x to the power 1, right? And so the second derivative here, I'm trying to do this all in notation of the series just so that you can see how this is done. Of course, you could take the derivative up here of this polynomial, but then you need to just make sure in your mind that whatever pattern you find continues on. So I'm doing it to the general term, basically. So anyway, we take this derivative. N is still 1 here. Negative 1 to the n. Then what happens? 2n is still here. We multiply by the next term. That's 2n minus 1. And we have x to the 2n minus 2, right? And what happens down here next? We have 2n factorial still, right? 2n quantity factorial. And let's try to simplify this. Remember our goal, we know the goal. So on these problems where you're trying to like prove something or show that a formula is true, you know the goal. So we know that what we should be able to show is that the derivative we computed is exactly the same as what I just highlighted right there, the power series formula for the function itself. So let's do it. To do it, we need to look at a couple things. First of all, 2n quantity factorial is equal to 2n times 2n minus 1 times 2n minus 2 factorial, and 2n minus 2 is 2 times n minus 1 quantity factorial, right? So why am I doing this? Well, I want to cancel. If I want it to look like this, I need to cancel these terms on top, right? Same thing here. X to the 2n minus 2 is the same as x to the 2 times n minus 1. All right? And so let's write this out. We have this starting at n equals 1, going to infinity. Negative 1 to the n. 2n, I'll write it out in a couple steps, I guess. This is x to the 2 times n minus 1. This has 2n minus 1, 2 times n minus 1 factorial. And we see cancel, 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 right? And at this point, what we can do is we can make a shift of our index. So we can, well, let's write out the first few terms, right? When n is 1, this gives us minus what? When n is 1, we get minus 1. Then when n is 2, we get plus x to the 2 over 2 factorial. And then it's going to be minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial, etc. Okay? And we compare, and look at this and this look very similar. All right, they just have opposite signs. So it looks like we've got this all right. But again, we need to make sure that the general formula coincides with our intuition. And what we can do is we can make a shift, okay? We can shift this n down 1, all right? But that forces us to shift all the n's in the equation upstairs up by 1. So whatever change you make downstairs, you have to make the opposite change upstairs, okay? And this then becomes the sum. N goes from 0 to infinity. -1 to the n plus 1, shift it up 1, times x to the 2 times, that's just going to be n when we shift it up 1. All right, all over, same thing down here. This becomes 2n factorial. And at this point, we can see what needs to happen, right? We have our original function f has a -1 to the nth power. Our function here, our second derivative, has a -1 to the n plus first power. So we can take out one of those negative ones, put it out front, right? And we can write this as negative n from 0 to infinity. -1 to the n, x to the 2n over quantity 2n factorial. And so indeed, this is negative f of x. So it's just a lot of symbol manipulation, but what we've shown then is that the second derivative of this function equals the negative of the function to begin with. And at this point, you start to think about your knowledge, right? A knowledge of calculus. So we've just found a function whose second derivative is equal to its opposite sign, right? And we have two very, very famous functions that we are very familiar with that obey this property. One of them is cosine of x, and the other one is sine of x, right? So of these two functions, it's possible that one of them could be represented by this power series. However, whichever one it is, so by the way, there are areas of math where you will prove that really it's got to be one of these two. It can't, or some combination, sum or difference of these two. We're not going to get into that. We will prove that this is the power series for one of these in the next section, though. And it turns out that because the powers here are always even, right, then this power series is an even function. And of our two trig functions, cosine is even, sine is odd, right? Remember the graphs? Cosine looks like this, right? Don't hold me to the drawing here. And sine looks like this. Yeah, okay, pretend. The point is, sine of x is not even, it's odd. It's got rotational symmetry. Cosine of x is even because you can just flip it over the y-axis. It's got symmetry about the y-axis, right? And so it turns out, and we will prove this later, but we'll call this just a guess, all right, that this series, n from 0 to infinity, -1 to the n, x to the 2n, over 2n quantity factorial, it's a reasonable guess that this might equal the function cosine of x. Okay? Now, at this point, after you've watched this video, you agree with everything that we've done up to this point, what you should do is plot some of the partial sums of this function together with the function cosine and see what the partial sums, look like and see if maybe you agree with this hypothesis.